Okay, so welcome everyone. Today we're going to be discussing the nuclear safety and regulations. As you may know, we are the Russian Nuclear Education Ambassadors, and we are a project of Rosatom, a program of Rosatom actually, that tries to, not only acquire information about nuclear energy and share it with you, but also to show you how can you go to study to Russia and obtain the same type of information that we get, the same education. So with me are Colin Saua, who has a PhD in fuel cycle and radiation safety, and Julio de Oliveira, who is a student in PhD on nuclear technology. Okay, so we're going to talk about nuclear safety and regulations, and let's start with Colin Sawa, who is going to talk about radiation safety in medicine. Collins, the floor is yours.
Right, good afternoon. Please, can you hear me?
Yes, we can.
Good. So my name is Collins Ewua from Ghana, and good afternoon to you all from Ghana. I'll be talking about radiation safety in medicine. And as rightly mentioned, I am a PhD candidate in nuclear fuel cycle and radiation safety at the National Research Tomsk Polytechnic University in Russia. So let's get going on the slide. So for the purpose of this presentation, I'll be doing a brief introduction about radiation medicine and nuclear medicine in general. And then I'll talk about discovery of radiation for medicine. And then I'll also talk about some modern uses of radiation in medicine. And then we'll look at the principles of radiation protection in healthcare. And finally, we'll look at regulatory bodies in nuclear medicine practice. So in the next slide, usually when people hear about radiation and nuclear stuff, all they think about is nuclear weapons and all of that. But it is interesting to know that radiations and radioactive substances can be used for diagnosis and treatment of diseases and medical conditions. So because radiation can harm cells, this diagnosis or treatment must be carefully planned, precisely conducted to minimize side effects according to established safety standards. So generally in the nuclear medicine practice or in the use of radiation to treat or diagnose medical conditions, there are strict safety standards that are supposed to be adhered to. Next slide. Next slide, please. So basically, I will walk you through two scenarios where discovery of radiation medicine was done. First was with Roentgen, who accidentally discovered X-rays when he was working in his lab, and he realized that a crude cathode tube had some radiations that were being emitted from it. For you to know, this crude cathode tube were shielded, and for that matter, there was no reason for any radiation to be able to penetrate. But he realized that these radiations were able to penetrate to form images on some light-sensitive paper that was closer to the whole situation. And so he began to experiment with it, and even took pictures of his wife's skeleton, or whatever you want to call it, with this radiation, and it was possible. So this radiation basically could sort of penetrate the human body to view what is inside of the human body. And after that discovery, a few years after that discovery, Marie Curie, also working in her lab with her husband, discovered polonium and radium. And these elements are also used to destroy tissues. So from there, they started using it to treat cancer, tumors, and all of that. So that is basically about how radiation medicine or nuclear medicine began. Next slide. Next slide. Next slide, please.
Do you see the next slide?
Yes, I can see the slide now. So presently, there are some, the radiation or nuclear medicine has undergone a lot of adjustments. No. Please go back to the previous slide. Please go back to the previous slide.
It is already showing.
Yeah, I can see it now. So nuclear medicine or radiation medicine has undergone a lot of technological advancements, and now in the present day we have equipment like the linear accelerator, which delivers high energy X-rays or electrons to the region of the patient's tumor. And then we also have another equipment like the single photon emission computer tomography, that's the SPECT, which is also a form of gamma camera or a special camera that rotates to detect radio tracer in 3D pictures. So basically the linear accelerator is used for therapy or treatment of cancers. And then the SPECT is used for diagnosis of cancers and other medical conditions. And we also have radiopharmaceuticals, which, for example, lutetium-177 is used for the treatment of prostate cancers. And then we have the technetium-99, which is used for diagnosis of cancers. So that's basically how far medicine has improved in terms of radiation or nuclear medicine. But all of these, and these are not the only equipment or technology we have. We have a lot of them, but this is just something to let you have a scope of what is happening. But then all of these equipment or technologies are strictly adhered to when it comes to safety principles. For example, when it comes to principles of radiation protection in healthcare, the IAEA, which is the International Atomic Energy Agency, has what we call the basic safety standard. So the basic safety standard is a book that gives how safety standards are supposed to be adhered to when you are treating or when you are diagnosing a patient with in terms of with nuclear medicine or radiation medicine. So first of all, we know that there will be normal exposures. That the normal exposures are supposed to be the radiations that are emitted onto the cancerous tumors, and so those ones are controlled by restricting the dose delivered. So if you have to deliver a dose of, let's say, 15 MeV, you have to deliver it precisely, and you don't have to deliver more than that. And then we also have potential exposures. Potential exposures are the ones that are likely going to be emitted into the space where the treatment is being done. And so those ones, it is recommended that the therapist put on protective equipment and other technologies that are supposed to block the radiation from having an effect on the second party or even the third party. So all of those standards are in this the basic safety standards of the IAEA. And also the ICRP, there is what we call the ICRP principles of radiation safety. Now, these principles talks about justification limitation, and optimization. So justification sort of proposes the idea that if there is any decision you are taking about or with regards to using the radiation for treatment or diagnosis, it shouldn't cause more harm than good. In other words, if you look at the situation and you can use radiations, the radiation is supposed to be more beneficial than causing harm, depending on the situation. And also, you should also limit the doses. So the total dose of any individual, or the total dose that are supposed to be used for the treatment of any individual or any patient, should not exceed the appropriate limits that are recommended by the ICRP. And finally, we also have the optimization, which means that every legitimate exposure should be as reasonably achievable or as low as reasonably allowable. So what it means is that if you, like I mentioned before, if you have to use 10 gray of radiation in a treatment of a certain cancer, you don't have to use more than that, because you have to use as low as reasonably allowable. And so finally, we'll talk about the regulatory authorities that regulates the nuclear medicine practice across the globe. So we have what we call the UNSCIA, which is the United Nations Scientific Committee on the Effects of Atomic Radiation. So this committee compiles and make assessments and disseminates information on the health effects of radiation. And they also compare the level of radiation exposure due to different sources. For example, if you look at thorium, thorium has a different threshold as compared to uranium. So they bring all those values, which are supposed to be the minimum values that are supposed to be met. And if you exceed that, that means that the exposure will be more harmful to the living organisms that are around or that are present in that environment. And then we also have the International Commission on Radiological Protection, which is the ICRP, which we talked about. Basically, they provide recommendations for protection and taking into account the scientific information provided by the UNSCIA. So UNSCIA will give you the information that are, and they give you the information, the minimum values that you are not supposed to exceed when it comes to the radiation dose. And then the ICRP also gives you recommendations as to how you can protect against in case there is an exposure that is more than the minimum exposure. So IAEA is also one organization that is based on ICRP recommendations. So what they do is they define the basic safety standards. If ICRP is recommending that you have to do this in order to protect against the radiation, IAEA will give you the basic safety standards, which is a comprehensive document of how exactly you are going to carry out that initiative. And also basically in the local setting or in the in-country setting, when you go to every country, there are regulatory authorities that gives that regulates the operations of nuclear medicine practice. So that is what the local authorities also do. They also regulate the nuclear medicine practice in the country, depending on what is supposed to be needed in that country. And so that's it. Thank you very much.
Thank you, Collins. That was very educative. And going on, I would like to kindly remind you guys that you can check our platforms via Facebook, Instagram, VK, or YouTube, just scanning the QR code that's here. And continuing with our event, we have our next speaker, who is Julio de Oliveira. Julio is a student a PhD student in nuclear technology, and is going to talk about nuclear reactor safety analysis. Julio, the stage is yours.
Hello everyone, good night. I am Julio and I'm going to talk about nuclear reactor safety analysis, which is one of the tools that we use to review if a reactor is actually if it actually is in order with the international regulations and if it can be operated on other nuclear facilities too. So the basis for all of the reactor and nuclear facilities operations is the International Atomic Energy Agency safety standards, which are the framework to develop the national nuclear standards. National nuclear standards are what we call the national regulations, which are based, like Collins was just talking about, on SCARE and ICP and other international agencies that create those standards, and then the countries use their own nuclear agencies to transform those in laws. Regulations themselves are not laws. You can have a different regulation in your country than the international standards, but that's not very common because those international standards are done for reasons. Like they are researched and they are proposed by people that did several experiments and research on how what is the best way to create those standards. So what is the safest and most efficient way to build a nuclear facility? So despite they not being laws, nuclear inspections, for example, in case of countries that are signatories of the Non-Proliferation Treaty, they still have to comply with the international treaties. For example, if you are a signatory of the Non-Proliferation Treaty, you have to prove that you are not enriching uranium above the standards. So in that case, they are going to be laws, but that's because the country, when they sign the treaty, they transform that in a national law. It's not that other countries can create regulations that force other countries to comply. They only comply if they agree to, and then they pass it to their own nuclear agencies or other governmental bodies that control this. So the adherence to the nuclear conventions are transnational, because if you are agree to them, then that means you are a part of it. So next slide, please. So here are the basic tools for nuclear safety analysis. This is the book of Dillon, Safety, Reliability, Human Factors, and Human Errors in Nuclear Power Plants. This is a very good starting point for nuclear safety analysis, because it kind of streamlines everything you need to know about the subject. It doesn't have many of the more deeper subjects, but it's one of the best starting points, and it's the bibliography used in Russia to study nuclear safety analysis. So with the equations and softwares, you can start to do actual risk analysis. So the softwares that are most common are Sapphire, which is free, Risk Spectrum, and Agona. Sapphire is free, so that's why it's often used by students, because we don't have to pay it, but the other two are also used by companies and universities everywhere in the world. So next one. Here are some of the equations. I didn't go too deep into them. I didn't use all of them, but those are two of the most common ones. That is the binomial distribution and the exponential distribution. So there are several probability distributions, and each of them make you able to calculate what are the probability of an event to happen, or how long until this event to happen. For example, with the exponential distribution, you can calculate how long will part of the reactor or equipment will last. Now, for the binomial distribution, it measures individual success cases. So, for example, the flip of a coin, what is the likelihood that you get head or tails, for example? For a reactor, that would be if you have several pieces of some equipment, how many of those will survive after the specified average lifetime. So since they are different, they're used for different purpose in calculations, can be mixed when you are doing the safety analysis. So the right side, you can see the logical diagrams. Those are very simple example diagrams. They work very similar to electricity, to circuits. So you can have series associations and parallel associations. Series associations are a case of equipment or processes that if one fails, all of them in the same chain will fail. So they are less safe. So you can always, if you have a problem with them, it always means a problem to the whole process chain or to the whole equipment, how altogether the operation. And the parallel associations is the case where we have redundancy or parts that work independently. So if one of those fail, the other ones will continue operating normally. Well, maybe with reduced efficiency, but they will still go on. Some of them are made specifically for redundancy. We see that a lot in airplanes, where redundancy is very important. The airplane has to survive several mechanical and electronic failures in order not to fall. And also nuclear power plants have a lot of redundancy in them, so they can always work. And there's also some pieces of equipment that are just not related, and then they are parallel associations because they are not needed for the operation. But if they are working, they will improve the efficiency of the other parts. So those are also parallel associations. And if all of them fail, then the system shuts down. Next slide, please. So I was trained to use Sapphire, so that's why I'm going to talk more about it in terms of nuclear safety analysis tools. So it has several advantages over other types of softwares. I include that it is free. It's very intuitive. It's easy to use. And since it's free, all of its documentation is available in the internet. So it's easy to find both official documents that explain how it works and also communities support for people that are using it, since it's more widespread. And here you can see it's a very old tool, so it has this kind of old-fashioned main screen, and that's because it's actually being iterated over several decades of development, which means that it's also very reliable because it's been used for decades and it works for its purpose. So here you can generate fault trees, which are like the diagrams that I showed before, and I will show later how they actually look on Sapphire. They look at ugly, I got to tell you, but they are very functional because they are with this. All of these probabilities and other abstract mathematical functions became visual, so you can understand just looking at them what depends on what and what is the probability of something, and also make all of the pertinent calculations. So you get numbers for your probability or average lifetime and mean lifetime of the equipment. So that's why it's a very powerful tool. It simplifies a lot of the work that needs to be done when you're doing calculations. It's also used by several universities and companies, including MEFI, NASA, and the ICRTP. Next slide, please. So here you have a particularly huge fault tree. This one is not an example. This is an actual fault tree of a space reactor. I did research on it. And here you can see that we have both parallel and series associations, and all of them are connected by a parallel association that leads to the final one, and the final one is the working reactor, the whole reactor working. This is for one part of it. The overall scheme of the reactor is much larger, but this part can display both parallel and series association, and in the sense that, for example, if one of those in branches fail, the reactor continues to operate. But if many of them fail, not all of them, many of them fail, then it will start to have problems. And this is one of the things that make it different, because for this, for example, I had to change the probability distribution because it's not obvious that which one you can use. You have always to think through for every kind of situation, which kind of probability distribution you're going to use. That's very debated. Because in this stage, it becomes more abstract for some cases. In most cases, it's very obvious, but not in all of them. And here I have one of the cut set results, which calculates the probabilities. This is quite simple compared to what Safari can do, but it's still complex in terms of what it actually done for me. So here I got the probability of failure per day of the reactor working. So, and that was very small because it's expected that the reactor will operate for several years without a problem. So that's one of the uses that you can use with Sapphire 7. Next slide, please. Another example from the same scheme, from the same reactor, but that's a different part of it. And here you have the larger set of parts. They are all parallel. You can see it here. So the fact that they are all like this means that it's very reliable because you can have some of them failing without impacting on the overall working scheme of the reactor. And here you have individual failure. It's visible in the other you have to, but it was so zoomed out that it's difficult to see. Here you can see then closer. And then you can have the individual failures. They are very, very small, each of them. And that means that if each of them is small, the probability that all of them will fail is extremely small. But if you have them in series, that would be not exactly the case. Of course, it's better to have smaller failure, but a lot of series pieces that are connected with failures will add them up, and then they will start to increase the probability of failure. And even if each of them has a small probability of failure, the whole set of pieces will have a large one, larger than the smaller part of it. So it's even worse than a chain, which the weakest link is the strength of the chain. In a series association for failures, that's not the case. It's worse. The weakest link is the major influencer in the factor, but it's not the combination of failure of them all is larger than this, so it's even weaker than the weakest link. So next slide, please. No, sorry. So the outcomes that come with the nuclear safety analysis are that with the analysis, you can decide whether a nuclear facility can be built or used. Basically, you can define if it is safe according to your understanding of what is safe, because that's also one of the factors that we have to consider. As we've seen, international regulations, and usually you try to comply to them. They have standards that say how much some of the failures are acceptable, how much probability of accident is acceptable, and how much and how you should contain them. For example, how to decrease the probability of those accidents to happen, and how to calculate how this likelihood of them to happen. This is all defined by international standards. So in the case of the reactor used in the example, the space reactor, it had 96.4% reliability over 17 years. That means that it had 96% of chance of working for 17 years, which for me, personally, it was considered to be quite fine. That's reasonable. That's very likely to work. Like you have 3.6% chance of failure. So that's very low risk for me. But for the American government, which is the builders of the reactors, that was considered too high chance of probability. So 96% success is too low for them. That means the reactor project is going to be revised so that it can provide safer margin of success. So they want to increase this number to a higher number. It's still unspecified, but they want more than 96.4% reliability, which is very reliable. They don't want to gamble, not the least bit. They want the most safe reactor possible. So the safety analysis help to estimate extreme scenarios. So you can also change things, for example, to see how a power plant, what is the likelihood that a power plant will have a failure if you have an earthquake, or if you have accident, or after one of the pieces has some failure, even if it's unlikely to happen, you can also make the calculations to understand how it will behave in those circumstances. So these also lead to policies and regulations to be created, adjusted both by the international authorities and by the national organisms that control this. So those are researched individually, and in many cases, findings by some of the national agencies are carried over to the international ones. So you can propose, for example, regulation where it's not specified, or to update current regulations if your country have some research findings that would improve safety as a whole, or if you find out some new method to do something and would like the new international standard to be this one, you can propose it to them, and they can choose if they will accept it or not. Well, usually if it's a better idea, they will accept it, but of course there's also political reasons for them accepting or not some new proposals, but those are all discussed between the specialists. So there's no universal analysis method or regulation standard. You always find some controversy and some different opinions on what is the best method, what is the best probability function, or what is the best standard as a whole. For example, some people will not like some of the standards used. I think that in the larger physics schemes, we can see that. For example, Americans don't use the metric systems. They don't like the metric system. We can force them to use it. So they will use different ones, and that means that all of the regulations will base over that. And for nuclear, it's the same. There is the equivalent of the metric system for nuclear frameworks, and those can be accepted or not by the countries. So even if the risk of an accident can be estimated, safety analysis is only one of the tools used for that. So it's limited to no information. Sometimes there is some information you don't know. For example, sometimes it looks obvious that if some of the pieces stop, the other one will stop, but in fact, it's not the case, or the other way around. And those can lead to unexpected accidents. Famous accidents always include some kind of human error in terms of planning the safety analysis. We have, for example, Fukushima, where they didn't consider the risk of taking the reserve generator underground. And since it was underground, it was more likely to be flooded. So the actual failure rate of it in case of a tsunami or earthquake was much larger than expected, that led to accident. So those are some of the cases. And also that means that we are unable to actually predict the behavior of nuclear facility. They are estimates, so we can have the general idea of what it would be like, but we don't have certainty that it would happen. For example, in case of the reactor that I was talking about, 96.4% reliability means that it is very likely to succeed in its mission for all the information we have about it, but does not guarantee that. Even if it was larger, if it was 99%, it would still have probability of failure, because all things have probability of failure. So that is one of the aspects of it. You can never be sure of what is going to happen. That's why we do so many estimates, and that's why it's so discussed. So of course, the larger the reliability, the better you trust it, because you always know that you have unexpected issues, and also some things that doesn't look that will work actually ends up working in the end. But those are also gambles. We are never sure enough about it. So next slide, please. So yes, that concludes the presentation. Thank you for the attention. Here we have some of my related entities that I am part of, like the Hackerspace from the University of São Paulo, MIFI, the National Institute of Energy and Nuclear Science, and the Latin America Nuclear Energetic Geopolitics Observatory in Brazil. So those are parts of IAN, institutions that I am a member of. And here you can also have a QR code, so you can scan, get to my link tree to get more information if you want to know more about nuclear security or other nuclear related information. Thank you for your attention, and thank you also, Daniel, for moderating the section.
Okay. Thank you very much, Julio. And okay, guys, well, this concludes our presentation. So if you have any kind of question, feel free to leave it in the comments. And also, well, I remind you to follow us on our platforms, Facebook, Instagram, VK, or YouTube by scanning the QR code. Thank you very much, and we'll be in touch.